Welcome to all in this video lecture. I am Dr. Amit Biswas from Agriculture Engineering Department and Haldia Institute of Technology. So today I am going to deliver lecture on continuity equation and what is that basically and what is the basis of continuity equation, and along with this the derivation of three-dimensional continuity equation will be solved here. So let me start. First is what is continuity equation. Suppose two sections are here. That is number 1 and that is number 2. So as we all know that, what is discharge first? So we all know that Q is equal to is discharge that means volume per unit time. That means V divided by its T. So for unit time, how much volume of water is flowed? It is basically the discharge. So here, in case of continuity equation, law of conservation of mass is followed. So what is that basically? At first, at section 1, suppose area is equal to A1, V1 is equal to velocity of flow, at section 1. Same here for section 2. A2 is equal to area, V2 is equal to velocity at section 2. And for one particular fluid, density will be fixed. That means at section 1, it will be rho. At section 2, it will be also rho. So, at section 1, is the mass M1 is equal to rho A1 V1 for unit time. At section 2, M2 is equal to rho A2 into V2. So according to the law of conservation of mass, it is M1 is equal to M2. That means rho A1 V1 is equal to rho A2 V2. As this is the same fluid and incompressible fluid, so that means rho will be same and both sides it will be eliminated. So ultimately the equation will be A1 V1 is equal to A2 V2. What is that basically? A1 and V1. A1 that means the area, V1 means it is velocity. So it is Q1 and it is Q2. So it is our continuity equation. Q1 is equal to Q2 at section 1 and at section 2 both will be same for the any fluid according to the continuity equation. So it is the fundamental thing of continuity equation. Now I will derive three-dimensional continuity equation for any fluid element. So what is that basically? Let me draw first one fluid element or as a control volume it is control volume. It is one kind of fluid element, it is control volume. So let me define first section. It is A, B, C, D section. Another side, it is E, F, G, H. So now, at first, it is a X direction, it is Y direction, and it is Z direction. So, along the X direction, the distance between A and E points, it is dx. Along Z direction, it is dz. Along Y direction, it is dy. So, suppose at first fluid is flowing through the x-axis, along the x-axis. So, from here at section ABCD, fluid will enter within this fluid element, within this control volume. So, it is the entering phase. So, now suppose density of fluid it is rho at section ABCD. Area of ABCD it is A1. What will be the A1 here? At first, we have to define the A1, the area of one section. So, A1 is equal to dz into dy. Now, velocity along x-axis. It is suppose U. So at section A, B, C, D, entering mass M input, it will be rho A1 into U, as it is along the x-axis. So rho U dy and dz. For it is the M in. Now in section E, F, G, H, it is the out section, it is the us leaving. So M out will be rho A1 U and summation of del x rho A1 U dx, as it is along the x direction. So what will be that basically? Rho U dy dz summation of del x rho U dy dz del dx. So what will be the mass gain within fluid element? So now mass gain that is M in minus M out. That is the expression 1 and that is the expression 2. So if I subtract from 1 to 2, it is M in minus M out. M in minus M out. It will be minus del x rho U dx dy and dz. It is the expression number 3. So it is for x direction only. It is for x direction only. Now, in same fashion, along y direction and along z direction, gain of mass will be calculated. Suppose in y direction, velocity of flow v, small v, and in z direction, velocity of flow, it is small w. So now it will be in y direction, mass gain it will be del x rho v dx dy dz. It is the expression number 4. In the same way, in z direction, it will be del x rho w dx dy and dz. So what will be the resultant value of mass gain? So we have to sum expression 3, expression 4 and expression 5. So it is that L del x rho u dx dy dz del y rho v dx dy dz and del w dx dy dz. So the ultimately equation is that L del x rho u L del y rho v del z rho w. Dx dy and dz. It is the expression number 6. Now, according to the law of conservation of mass, here is the gain of mass and the rate of change of mass per unit time will be same. So, what is the rate of change of mass per unit time within this control volume? Rate of change of mass is equal to del m del t. Now it is What will be the aim? It is rho dx dy dz. That is the expression number 7. So now, according to the law of mass and its conservation of mass, that is equation number 6 and equation number 7 will be equal, same. So what will be that? Basically the resultant equation. In both sides, it is dx, dy, dz will be eliminated. So ultimately the resultant equation is del rho del t L rho u Lx del del y rho v and del del z rho w will be equal to Sg. So it is general three-dimensional continuity equation for fluid flow. It is the ultimately equation of three-dimensional continuity equation. That is expression number 8. Now, if we consider incompressible fluid, that means rho will be fixed and steady flow. That means if steady flow and incompressible fluid, it means del rho del t will be 0 and ultimately equation will be del u del x del v del y and del w del z will be 0. It is for three-dimensional incompressible fluid for under steady flow. It is expression number 9. And if it is dimension in 2 dimension and 1 dimension, so 1 dimension will be eliminated for 2D cases, it will be the resultant value of del u del x as del v del y is equal to 0. So it is that continuity equation and its three-dimensional equation derivation, and along with some specific condition under incompressible fluid and steady flow. So it is all about continuity equation and its derivation. Thank you very much.